Yeah, and then, as I said before, stops and moves, the computation of stops and moves are the most important parts typically. So there are, again, different approaches. Just to sketch two of them here. The first probably pioneering approach here, also in 07, back in 07, is the SMOT approach, stop and move computation. The authors here define a candidate stop as a tuple of the geometry of the candidate stop, so that is the spatial feature type, and the minimal time duration. So R is typically a region, like a coordinate with a radius, but need not to be, can be also a rectangle or stuff like that. Delta here is the time duration, the minimal time duration. A trajectory has to stay within this region in order to define a stop. So a stop is defined as a region, and or as a region where a trajectory or several trajectories stay in a minimum time duration, and those two things are defined here by the region and the time threshold. So for example, a given hotel region around the hotel for 3 hours would be, for example, a definition of a stop. And then we also need an application, because we can then add some application-specific semantics to a stop candidate. So an application is a finite set of candidate stops, with non-overlapping geometries. So the regions here are non-overlapping, and we give them a specific semantics. So for example, this candidate region here, or the region of this candidate stop, is a hotel, and this region here is a museum. So that is a application specific interpretation of a stop candidate, where you typically just have a geometry and a time threshold. And if you add some semantics to this region here, you have an application-specific semantics or application-specific interpretation. So now, a stop of a trajectory with respect to an application is a tuple, so a region and a time interval, such that this trajectory intersects the region at all time slots between this time in this time period, actually, which makes sense somehow. And a move of t with respect to an application is then a maximum contiguous subtrajectory of t, either between the starting point and the first stop of t, or between two consecutive stops of t, or between the last stop of t and the end point of t. Well, that makes sense. Or of course the trajectory itself if t has no stops. So if you have the start, so this is a trajectory here, you have the start point here, you have identified a stop here, and a stop here. So everything between the start point and the first stop is a move. Everything between first stop and the second stop is a move, and everything between and so on and so on. Okay, you see, I see you get the point. So that is basically the idea, the definition, and the question is how to, well, you can, of course, given some thresholds here, especially for the time interval, you can compute that easily, and then you, so you can compute easily the stops from each trajectory, and then, if you have the stops, of course, you have the moves also. So this is just from the trajectories, from the raw trajectories, so to say. And there is an extension which is called the cluster-based SMOT, which tries to cluster the trajectories based on speed first. So instead of just looking when is a trajectory in a given region for a given time slot, they also try to or they try to consider the speed of a trajectory, and if a trajectory has a low speed, it is assumed to be at an important place. And the algorithm is quite similar to SMOT, but clusters trajectory points first, and then adds semantics to the clusters. Other than the SMOT algorithm directly. Yeah, and that's it actually for this very short overview on trajectory mining. So here are some further readings, the original papers or the references to the original papers we have covered, or we have just glanced here. We not really went into detail. So if you want to find the details, just go into this or just yeah, read into those papers here. And yeah, I hope you are inspired a little bit. So you see those references are a little bit older right now. So as I said before, this application field, or this research field has accelerated over the last 2-3 years a lot. And it's really hard to keep track here. So yeah, if you're interested, then try to catch up some of those recent papers here from the same from those venues here. They are good venues, so then you can see what people are doing in this field right now. Anyway, that was it. So we are at the end of KDD2. I hope you enjoyed the whole lecture, even though the setup was not probably not optimal. So also for me, I really regret that we cannot really meet in person. I cannot tell you too many stories, side stories about KDD things. It's easier to do that personal in the lecture room than on the podcast, because yeah, then in the lecture room you can just fall asleep in that case, but that's a little bit harder with the with the podcast. But anyway, I hope you enjoyed it, and yeah, all the best for the exam. I hope you somehow prepare yourself considerably, so please do that, because I'm happy if you all pass, but of course we have to be a little bit critical in that, but we will be happy if you all pass. But anyway, so yeah, stay healthy, stay tuned, and as I said before, all the best for the exam, and all the best for the remaining semester, and so on. See you guys.